That stuff. We have quiz due on Monday. No quiz on Friday. No quiz Friday. So we have the slightly less exciting quiz Monday. Okay. The quiz doesn't cover as much. Not as many questions. Many of you have already looked at the questions. Reading is shorter. There are really two main things that we're going to have on the exam from Chapter 3, and that's graphical addition of vectors. I'm going to go over that today. And then a numerical addition of vectors. Being able to add vectors graphically, which the reading goes into that, and I'm going to show you how to do it today. It's not that hard, it's just drawing triangles, really. And then numerical addition of vectors, which really just gets into trig, knowing your right angle trigonometry, which we've already covered. So there will be some new stuff, but largely it's going to be stuff that we've already seen a little bit. Test is on Wednesday. The test is going to be in this room, right? No. Where is it going to be? The auditorium, the big auditorium in Pelcha Hall with the big comfy seats. You ever been in that? Yeah. You'll have assigned seats. There'll be a sign outside the door that has your seat number on it. Please make sure that you get in the correct seat. It helps me a lot. What's that? Yeah, they usually have orientation there. Right. The exam will be about 25-ish questions long, give or take a couple. You'll have an hour, not 55 minutes. You'll have a full hour. You need a calculator, no equation sheet, none of that jazz. You will have a form that I'll give you, and I've already shown you how to fill that out. So if you have questions about that, let me know. Do you have any questions about the exam coming up?
So we don't need a Scantron?
No Scantron, Rachel. No Scantron at all. It'll just be stapled to the front of your test, and you'll rip it off, and then you can write on the test, and you bubble in your answers on the form. Y'all excited? Nick, you're excited?
Will it be all of Chapter 3 or just the front portion?
Just a little bit that we're going to cover today, and then we'll get all the essential stuff today, and then, on Monday we'll wrap up details and stuff. And we'll have time on Monday to also answer questions. There is a help session too on Tuesday at, 12:55, I think. Sorry if that doesn't work for you. That's just sort of the best time I can get. I'll record it and post it online in case you can't come. All right? Okay. Well, let's get started on Chapter 3. Vectors and 2D motion. We've already talked about vectors a little bit. Vectors have magnitude and direction. Scalar quantities have magnitude only. And we talked about before what are some vector quantities, velocity, acceleration, displacement. And then we talked about what were some scalar quantities, time, mass, etc. Anything that doesn't have a direction associated with it. We usually draw vectors with an arrow. So if I draw the velocity vector or represent it as a variable, I usually draw it with an arrow over it. Though as you know, we tend to sort of lose that as time just because, I don't know, it takes a lot of time to draw that little arrow. But we usually draw it with an arrow over it if you have a force vector along like that. Now we can represent a vector graphically, because remember, a vector has a magnitude and a direction. We can represent both of those by drawing an arrow like this. So we can draw an arrow that represents both the magnitude and the direction. The magnitude is given just by the length of the arrow. So if I make the arrow shorter, it has less magnitude. If I make the arrow longer, it has more magnitude. The length gives the magnitude, and then the direction is the direction that the arrow is pointing. So the length of the arrow gives magnitude. Sorry, that's misspelled. While the direction, and we have magnitude and direction, is just the direction the arrow is pointing. So let's say I draw two vectors. So I draw one vector that looks like this, and then I draw another vector that looks like this. So the smaller vector, this smaller little arrow, has the same what? it has the same direction. But about half the magnitude of the larger one. And it has half the magnitude because the length of this arrow is 1/2 the length of this arrow. So for example, if this was a displacement vector and this arrow represented 1 meter, it doesn't have to be 1 meter long, although it looks like it is about 1 meter long. It can be just a couple centimeters long, but it will represent an arrow that is 1 meter long. Then what would the length of this arrow represent, or the displacement of this arrow represent? A 0.5 meter displacement. So the length of the arrow directly is related to the magnitude of the vector. Two vectors are equal if their magnitude and the direction are the same, even if they're drawn differently in a different coordinate system. So I can draw a vector that has a certain length and direction over here, and that's exactly the same as a vector that's over here, or over here, or even if it's red. They're still the same, because they still have the same length and they have the same direction. You can move them around as long as you don't change their magnitude or direction. That's important when we get to the graphical method of adding vectors, because we'll take vectors and we'll translate them to other parts of the page. You can do that with a vector. It doesn't change the vector. I can take my vector and I can move it over here, or over here, or over here, as long as I don't change the direction, like that, as long as I don't change the magnitude, changing the length of that vector. You with me so far? Easy peasy so far, right? It doesn't get that much harder. Okay, for the geometric method of adding vectors, we're going to use the tail to tip, or sometimes this is called the triangular method, sometimes it's called the parallelogram method. But in this, we are going to draw two vectors. Let me go with that. We're going to consider, you can have two or more vectors, and you can add them up by placing them tail to tip. So you place vectors, two or more, tail to tip. Let me just show you a quick little example. Let's say that I have a vector here, call that vector 1, or I'll call it anything, a vector there, a vector there. I've placed them, the tail of one vector to the tip of the first vector. So I have these three vectors. If I want to know the sum of those three vectors, the sum will look like that. So if this is vector A, this is vector B, this is vector C, then vector A plus B plus C will look like that. We'll go through some examples like this, but you will need to know how to do this in order for the exam, and I'll show you how I'll phrase those questions and how I'll present them to you. So let's consider two vectors, A and B. Let's say that vector A looks like this, and vector B looks like this. You can find the sum by placing the vectors tip to tail, or excuse me, tail to tip. That's the tail of the second vector to the tip of the first vector. Right, this is the tail, this is the tip. You place them tail to tip. So if I were going to do this, I would draw A, I would draw B, like that, and then the sum of those would be this vector. We'll normally call this the vector R, for example. R is equal to A plus B. If you're subtracting vectors, what are you going to do? So let's say instead, let's say that this is A and this is B. And I want to know what is the difference in these vectors, say A minus B instead of A plus B. Think about, what would you do? How would this method differ now? Typically, if we make a vector negative so far, what has that done to the vector? Don't say anything. What has that done to the vector if I have, say, something traveling in the positive direction and then I negate that direction? What happens to the direction of that vector? What does it happen? It flips 180 degrees. So what are you going to do here if instead of saying A plus B, right, A plus B is I would bring these tips and tails together and then draw a vector like that. What am I going to do with this negative? What is that negative going to do to my vectors or vector? Which one is it going to affect, first of all? Is it going to affect A, B, or both of the vectors? Only B. And what's it going to do to B? It's going to flip it the other direction. So if I want to know A minus B, the way I'll draw that is I'll take A, I'll draw it up here. Remember, because I can do that to vectors, I can move them around wherever I want. And then I'm going to draw B like this. Or it's not B, it's actually negative B. And then the sum of those, or rather the difference, A minus B, is going to look like that. So when you're subtracting vectors, you simply switch the direction of the vector that is negative. And that shouldn't be too groundbreaking to you, because we've been doing that all along. Positive is this direction, negative is this direction. They're 180 degrees off. Notice, however, when I did this, that I kept the length of B the same, and I also kept the magnitude of it the same. I just switched, kept the length, which is the magnitude, the same. Okay? You can do it for more than two vectors. I've sort of already shown you this. For the test, though, you only have to deal with two vectors. But you can do this for more than two vectors. You'll do this in lab. You'll have three vectors. Like, for example, in lab, let me give you a little precursor to what you'll do in lab. You'll add a vector that looks like this. You'll add a vector, another vector that looks like this. If I were to add those two vectors, the sum would look like that, right? Like if this is A and this is B, this is A plus B. But I can add a third vector, say this is C, then the sum A plus B plus C would look like this. So this would be A plus B plus C. You're going to do that exercise in lab. You're going to add vectors A and B and find that it's this vector. And then you'll add a third vector, C. Notice still using the tip to tail, tip to tail, tip to tail. And then here's the tip of C. And then the resultant, or the sum of A, B, and C is like this. You'll have two questions that are graphical addition of vectors. Is that right? I think so. All right, let's do a little quick quiz. So magnitudes of A and B are 12 and 8. If A plus B equals R, what are the maximum and minimum values of R? The magnitude of A is 12 units, whatever the vector A represents. The magnitude of B is 8 units. The sum, A plus B equals R, or A plus B is equal to R. What are the maximum, or excuse me, which of these is an appropriate answer for R? I'm sorry, this should say, which of these values is appropriate for R? But in the course of that, you need to think about what are the maximum and minimum values of R. Magnitude of R has a value. Only one of these values will work. Which is it? Ask your neighbor if you like. think about how the vectors can be arranged. I haven't given you anything about the direction of vectors A and B. So how can they be arranged? Stop in about 10 seconds. Stop at 140, 140. Okay, A is right. You have two possible, or you have two sort of boundaries for what A plus B can be. The maximum is that you have A in this direction, and then what direction should B be in order for R to be at its maximum value? Should it be in the opposite direction, in the same direction, or somewhere in between? It has to be in the same direction to get a maximum value for R. So if I put B here, then R is going to be there. Right, since A is 12, B is 8, R has a maximum magnitude equal to or less than 20. It has a minimum, if this is A, and B would be in this direction, and so R would have a minimum greater than or equal to 12 minus 8, or 4 units. So the magnitude of R has to be somewhere between 4 and 20. None of these are between 4 and 20, so it has to be A. Let's try this one. Here's two vectors. Zoom out so you can see the whole thing. Here's two vectors. What is the resultant of the difference A minus B? This is A, B, C, and D here. These are your vectors, vector A, vector B. I want to know which of these vectors represents the difference A minus B. So you have to do a graphical addition of vectors A and B. Which of these is equivalent to A minus B? Couple of guidelines for you. Don't forget something's going to happen to one of these vectors because we're doing a difference. And then the other thing is that you want to make sure that you draw tail to tip. You're drawing the tail of one vector to the tip of the next vector, of the first vector. The tail of the second vector to the tip of the first vector. All right, we're a little all over the board. That's okay. We'll do some more practice like this. I'm going to stop in about 10 seconds at 1:30. 1:30? Sorry, did you get it in? That's okay. All right, D is right. D is right. But we're still sort of all over the board. But don't sweat it. You'll get it before we leave today. So I draw A first. There's A. I have to negate B. So that means I draw B like this. This is negative B. And then I start at the beginning of A, and I draw it in that direction. So D is the right direction. D is right. Let's see, a lot of you probably put B too, right? Yeah, that was the next most popular answer. I always like to think of this in terms of displacement. Like, this is my beginning point, and this is my end point. Displacement is a vector, so I can think about this with displacement. This is my beginning, and this is my end. So I can take two paths to get from the beginning to the end. Either I can take this path, which is A minus B, or I can take this path, which is also A minus B. But it's always going to start at the beginning and end at the finish. We'll always start here and end here. And then that'll help you not to fall for this trap, because this is not the right answer. William?
When you draw an R, you always start from the beginning.
That's right. When you draw R, you always start at the beginning, because that's your beginning point. And then you always end at the end. So that's your ending point. Okay? Yeah. Let's try this one. All right, I'll stop at 55. 55, so about 10 more seconds left. A few more seconds, stopping in 2 seconds. Okay, good. This is just like the problem we did before. There's a limit between the minimum and maximum of R. The maximum is 25 plus 12, that's 37. The minimum is 25 minus 12, that's 13. So somewhere between 13 and 37. Ding, 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 right here, okay? That one's between 13 and 37. Let's see. Let's do this about components. So that's one part, and don't worry, we'll come back. I have some more clicker questions about adding up vectors and give you a little more practice with that. But let's look now at the numerical stuff that you're going to have to do. You'll need to know how to find the components of a vector, which is going to be very important in the second half of this chapter, and in chapter 4, and in chapter 5, and really for the rest of your life, like all through to the end of next year, to the end of the spring, I mean. Did y'all know that you take a second semester of physics? Did you know that? It's very exciting. Anyway, so the, what was I saying? Oh, the numerical addition of vectors. So you'll need to find the components of vectors. You have a question, I'll say, what is the x component of this vector? Or what is the y component of this vector? And then you also have to take two vectors and add them up numerically. So you'll have a question like both of those. When I say the component, either the x or the y component, I like to think of it as a shadow or a projection of the vector onto either the x or y axis. So if I have this vector A, it starts at the origin and a certain magnitude and direction. If I shine a flashlight on top of A so that it shadows onto the x-axis, I'll get a shadow of A down here. Y'all follow what I'm saying? It's like a projection onto the x-axis. If I shine a flashlight over here, it projects a shadow onto the y-axis. And so I get these x and y components. And this vector A, we're going to add to give you the original vector. So, I'm sorry, let's stick here. We'll come back to that. So, this is my vector A. I can take my vector AX here, that's the x component, and notice I can draw these just like this. So this is AX, and this is AY, and this is my vector A. So I can say then that A is equal to the sum of its x, y components. I just want to be very clear that what I'm not doing here is just adding up the magnitudes. When I draw the little arrows on top of them, it becomes not just a regular old sum, but it becomes a vector sum. So this does not mean that if this is equal to 3 and this is equal to 4, it does not mean that this is equal to 7. Y'all follow me? But what it does mean, actually, and you probably know what A is, what is the magnitude of A here? It's equal to 5, because it's a right triangle. So our sums here are going to be a little bit different. And we'll get to this, but our sum is going to involve our right angle trigonometry and our Pythagorean theorem. We'll get to that. Let's focus on the projections, or the x and y components. So don't forget your trig, SOHCAHTOA. You need to have that down pretty well. You'll have questions from chapter 1 that's just, I'll give you a triangle and I'll ask you, what's this angle or what's this side? Probably just one question that's based on our trig stuff. But it's going to be used for the rest of the year, for the rest of the semester at least, because we'll have it in chapters 3, 4, 5, 6, and I guess that'll be it. And then again next semester. So you really need to master the trig. Like you need to be able to look at a triangle and not have to even think SOHCAHTOA, that you just become the triangle. Okay? You get all pointy on 3 sides. But you really need to master that. And if you haven't mastered it yet, then please come see me. I can help you, or just spend the time on it too will help. So when we're calculating our x and y components, since our sine of theta is opposite over hypotenuse, this is my angle theta, so my opposite side is AY, and my hypotenuse side is the magnitude of A, then that means that AY is equal to A sine theta. You follow me? If I want to calculate what is AY, I can do that based on the sine of the angle theta. Because the sine of the angle theta is opposite over adjacent, opposite over hypotenuse. This is my opposite side, this is my hypotenuse, and so I can figure out what is that y component. So my y component is A sine theta. My x component, by a similar argument, that is cosine theta equals AX over A, so AX is equal to A cosine theta. You need to do better than memorize these. You need to internalize them. Like you need to be able to look at a vector and just say, gosh, that vector, the x component is A cosine theta. The y component is A sine theta, because we'll use it a lot in this chapter and upcoming chapters. Also, if I have the x and y component, I can find the angle of the vector A based on those x and y components, based on the definition of tangent. We did something very similar in chapter 1 when we did our trig review. Is this exciting? It gets better. Okay, let's do some quicker questions. We'll go to our concept test. This is in the back of your book if you have it. It's in the appendix. I'll post this on Monday, or I'll post, the first half of chapter 3. I'll post this on Monday. Two vectors are given such that A plus B equals 0. So what can you say about the magnitude and direction of vectors A and B? And the vectors A and B are they are non-zero. They have a magnitude that's greater than 0. All right, I'll stop at 1 minute. 1 minute, just a few more seconds. D, that's right. In order for A plus B to equal to 0, it must be true that they have equal magnitudes, but exactly opposite directions. Exactly equal magnitudes and opposite directions. Any other scenario will not give you a magnitude equal to 0. Right? Any other scenario will not give you a 0 vector. They have to be equal but opposite. Let's try this one. Two vectors such that A plus B equals C, and then also A squared plus B squared equals C squared. Looking at the magnitude, when we put these little pipe symbols around them, that means the absolute value or just the magnitude. How are vectors A and B oriented with respect to each other? All right. You're doing better than I expected, but you're still a little bit around over the board. I'm going to go to 103. 103. Okay, A is right. And this, we know it's right because, does this look familiar to you in any way? Pythagorean theorem. The Pythagorean theorem describes the relationship between two sides that are perpendicular to one another. So my vectors look like this. This is my vector A, and this is my vector B. And they are oriented such that C looks like this. This statement is true only if these two are perpendicular to one another. If they make up any other triangle, the Pythagorean theorem will not apply. And guys, as I said, you'll have 4 vector questions. One component, I'll ask you to find the x, y component. The other, which we haven't covered yet, I'll ask you to add 2 vectors. Another, where like a numerical addition, I'll ask you to graphically add. And then I said you'll have another graphical question. It's sort of something like this, where I have you think about the vectors. Nothing to calculate, but just think about how they're oriented with respect to one another. Now clear with me what that means? Okay, A plus B equals C. This is the vector sum, but it's also true that if you add their magnitudes, the magnitude of A plus the magnitude of B is equal to the magnitude of C, then how are A and B oriented with respect to one another? All right, let's do about 10 more seconds. I'm going to stop at 1 minute. Okay, B is right. The vector A plus the vector B are equal to the vector C. Right, but it's also true that the magnitude of A plus the magnitude of B is equal to C. So let's say that the magnitude of A is equal to 2, the magnitude of B is equal to 3. That means this is equal to 5. But notice that if I have A and B in any other direction, 2, 3, this direction is something less than 5. It's not equal to 5. Okay, so in order for this to be true and this to be true, they have to be situated like this, the vectors. If each component of a vector is doubled, what happens to the angle of that vector? I double the x, y, and the y components. What happens to the angle of your vector? All right, let's do about 10 more seconds. Exercise your geometry skills. I'll stop at 53. 53. Oh, 90%. Awesome. You want a story instead of a joke? Would you rather have a story or a joke? Story. You don't like my jokes? I was a real jerk when I was a kid. And I had this geometry class. This just reminds me of my geometry teacher. I don't remember her last name, but her first name was Ethel. And so, you can imagine somebody named Ethel. She's a really old lady, and she couldn't hear very well, she couldn't speak very well, and the kids in that class, we just messed with her a lot. And we would throw things at her, like pennies and quarters and pencils, and one time I threw a D battery at the board. She was writing on the board, so she had her back to me, and I threw it at the board, and that poor lady, what a jerk. I'm glad that y'all don't do that. What's that? Sorry, my view in your eyes is just right. Okay, it is right though. I think of that because you have these similar triangles. If I change my y component and my x component by the same amount, then I make the triangle bigger, but these angles still remain the same. And if you wonder about that, you can say, well, gosh, the theta is the inverse tangent of ay over ax. Imagine what happens if you double the y component and you double the x component. Well, nothing happens because it cancels out. Similar triangle. We'll do this one. The vector has x and y components that are equal in magnitude. Which of the following is a possible angle for this vector? Only one of these angles is possible. Which is it? The x and y components are equal in magnitude. All right, I'll stop at 50. Stop at 50. 50, just 2 seconds left. Okay, E is right here. Where'd I put C? Oh, 90. I know what you're thinking, but look, this is the deal. I have this x and y components are equal in magnitude. This is ax, this is ay. What you're thinking, those of you that put C, you were thinking this, right? But really, when we define the direction of a vector, and I hadn't said this earlier, so it's sort of my fault that you got it wrong. That this angle is the angle that we use to describe the direction of the vector A. So this angle is equal to 45 degrees. All right, we never use this angle. We use this angle, the angle from the x-axis that describes this vector. Don't worry, you'll get that. It's not a big deal. Okay, let me show you now how to add two vectors. So I'm going to fill this in because it'll become important in chapter 4, but you don't really need to worry about it for our test coming up. But in some cases, you might need to rotate the coordinate system. To make a problem easier, we selected the coordinate system here, but we could just as easily change our coordinate system to be not there, but instead to be here. And then I have one vector that's on axis and one vector that's off axis. In this case, the angle between the y-axis and B would be phi minus theta. Listen, don't sweat this right now. If you don't understand, don't sweat. It doesn't become important until the latter half of chapter 4, when we'll start rotating our coordinate system. Yeah, that's a phi minus theta. Phi, yeah, if you want to say phi, or phi, I like to say phi. Don't sweat this. Not important right now. Not important. Okay, this is important though because you'll need to do this on the test. To add vectors, you add their components separately. So let's say that I have two vectors A and B, and I want to take the vector sum. Now the vector R is also the sum of its components. That is, R is equal to Rx plus Ry. We've shown this already, right? There's Rx, there's Ry, there's R. The components then are the components of R are the sum of the components of A and B. That is to say, Rx is equal to Ax plus Bx, and Ry is equal to Ay plus By. Let me draw a picture for you to describe this. So let's say that I have two vectors, A and B. This is my vector A, and this is my vector B. This is my vector B. The sum of these two vectors is going to go from here up to here. So this is my vector R. Now, does A have an X or a Y component? It only has an X because it's on the X-axis. So this is AX, and it doesn't have a Y component. B, I can break into its X and Y component. So this is BX, and this is BY. Now, R has X and Y components too. This is Rx, and this is Ry. Notice here that Rx is the sum of Ax and Bx, and Ry is the sum of By and Ay, but Ay is 0. Similarly, you'll have a similar problem where I give you two vectors, one will be on axis, one will be off axis, and you have to do the sum of it, which I'm going to show you now how to do it. And you have several of these on your quiz. I think you have 6 or 7 questions, and several of those are adding up two vectors for practice. Very similar to what you'll have on the test. So let's say I give you these two vectors. One is 1 meter long and 45 degrees from the axis, and vector B is 2 meters long and 60 degrees from the axis. So if I were to draw these, I can just sort of sketch it out. Vector A, which I'll do in blue, is 1 meter long and 45 degrees from the axis. That means this angle is 45 degrees. And then vector B is 2 meters long, so twice as long. This is vector B. This angle is 60 degrees. Vector A is 1 meter, 45 degrees from the x-axis. Vector B is 2 meters, so twice as long, and 60 degrees from the horizontal. The first step is to find the components. AX is A cosine theta. AY is A sine theta. Again, you'll have a separate problem on the test where I just ask you to find the X or Y components. BX is B cosine theta. BY is B sine theta. This sort of helps me, it may or may not help you. X and Y, those are in alphabetical order, right? Y comes after X. Is that true? Cosine and sine, C and S. S comes after C in the alphabet. Isn't that true? It's either alphabetical. X is cosine, Y is sine. If that helps you, great. If not, that's fine too. So I can find these X and Y components. This is going to be 1 cosine of 45. That's the magnitude times the cosine and the angle. Works out to be 0.71 meters. This is 1 sine of 45. What does that equal to? Does anybody know right off the top of their head? 0.71, because it's an equilateral right triangle. So the X and Y components are the same. And then B cosine theta is 2 cosine of 60. Cosine of 60 is a half, so this is equal to 1. And then this is 2 sine of 60. Just remind you, I got the 2 here and the 60 here. And this is equal to 1.7. So that's your first step, is to find the components. Then you add the components. Rx, remember, is AX plus BX. That's 0.71 plus 1. Taking this, putting it right here, and that right there for 1.71. I'm going to keep more sig figs than I need for now, just to, as I said. Okay, and then Ry is AY plus BY. That's going to be 0.71 plus 1.7. And that's equal to 2.41. Your problem on the test will be slightly easier because one of them will be on axis, say vector A will be on axis, so you won't have this step right here. You won't have to find AY because it'll be 0. Or you won't have to find AX because it'll be 0. Because one of your vectors will either be on the X or the Y axis. Oh, another important, oh shoot, we're going to get through. Let me just point this out so that you know this over the weekend. As a little aside, sometimes our vector is in the second or third quadrants. So let's say, for example, I have a vector here. Say it's 1 meter, 30 degrees. I would say this vector is 1 meter at 30 degrees from the negative x-axis. Is my y component going to be positive or negative in this case? It's going to be positive. So AY, we'll call it, is positive. What about my x component? Is my x component going to be positive or negative? Negative. Negative. We'll get into this on Monday, where we have vectors that are in different quadrants, not just the first quadrant, but just for you to sort of keep that in your mind as you're doing the quiz over the weekend, if you do it over the weekend. Okay, so back to our original example. If I want to find the magnitude of R, I know Rx and Ry. I say the square root of 1.71 squared plus 2.41 squared. And that's equal to 3. I'll just go to 2 sig figs. And then if I want to know the angle, it's the inverse tan of opposite over, that should be Ry. Which is the inverse tan of 2.41 over 1.71, which is equal to 55 degrees. All right. We're going to do some more clicker questions on the concept test, but on Monday we'll do another example where our vectors are not in the first quadrant. But you'll have some, I'm pretty sure I picked some examples on your OpenStax quiz that have that. But they work out basically the same, except your components will either be positive or negative. You have to figure out which direction they are. Okay, let's go back to this. Did I tell you I had a test this morning? Yeah, I had to, it was a map quiz. I had to name 48 mountains, valleys, rivers, cities in ancient Palestine. Do you want to know how I did? How do you think I did? Awesome, is that what? Awesome. B, who said a B?
An A?
Not just an A. Really? You think I made 100%? I did make 100%. It was an easy quiz, though. Your test is going to be a little harder. You know, one or two of you might make 100%, okay, but it's going to be a tough test. I don't want to scare you. I want to scare you a little bit. But it'll probably be the easiest test all semester. Is that scaring you enough? Listen, you know what the test is like. Go look at those old tests. I pull some questions from your tutors, from your OpenStax tutor bit. You know what it's going to be like. Look at your homework, look at the concept test. No surprises. Oh, shoot. I guess we did them all. Did we do this one?
No.
It's 37. We've done it twice before. All right, well, let's start this other example, because that way it'll give us more time to review on give us more time to review on Monday. All right, so let's look at these vectors. I have three vectors, vector A, B, and C. You'll just have to deal with two vectors on the exam, but in chapter 4, you have to deal with 3 or more vectors when we do forces. So this is we're gonna build on this a lot. Vector A, there's its magnitude, there's its direction. Did I leave one mic? This. No, I threw a D cell. You know, the big batteries.
Why do you have that?
For my calculator or whatever. It's an old calculator. I don't know what I have it for. All right, so first job is to find our x and y components of all of our vectors. And this is where it's a little bit different. So my x component of A, I set up a little table here. You might do the same, you might not. It's going to be 2.236 times the cosine of 63.43. And that's equal to 1. The y component is 2.236 cosine, or excuse me, sine of 63.43. And that's equal to 2. We can do that for all of these. Vector B is going to be 5 cosine of 53.13. That's going to equal to 3 meters. This is going to equal to 5 sine 53.13, and that's equal to 4 meters. All right, well, let's draw vector B. I'll draw vector A and B. Here's vector A. Vector A looks something like this. Vector B, notice that it's 53 degrees below the positive x-axis. So vector B looks like this. So for vector B, which of its components, or maybe both of its components, are going to be negative? The x, y, or both?
Y.
Only the y, right. Because the y component of this vector is in the negative y direction. That projection is onto the negative y-axis. So this is negative 4. And then C works out this times the cosine of this equals to negative is equal to 2. And this is equal to 5. The vector C, notice, is 68.2 degrees above the negative x-axis. This is C. So which component of its is going to be negative? Only the x. Right, so that's a negative 2 there. And just to remind you, that I just got this 5.39 cosine of 68.2. 5.39 sine of 68.2 to find those x and y components. I think that's a good place. We'll stop there. I'll pick up on Monday. Okay, we will have some time to review on Monday. There's just a little bit left of this to do. Have a great weekend. Okay.
Wednesday.